Okay. We want to find the equation of a line in space, straight line. So we ask, what's the equation of a line if we know a point on the line, x naught, y naught, z naught? If the line is parallel to some known vector v equals ai plus bj plus ck, where I, j, and k are the unit vectors in the x, y, and z direction. Well, we can draw a picture. Here's the point x naught, y naught, z naught. And here's a vector v. Now we could put the initial point of the vector v at the point x naught, y naught, z naught. And we'll eventually do that. Matter of fact, we'll go ahead and do that right now. Okay, so let's say, get the direction right. Here's a vector v. Not perfect, it's not quite the right length, it's too short. Pretty much got the right direction, but I can see by looking at the screen that that's just a product of my lack of parallax there. So I'm just going to erase this vector v. And while I'm at it, I'll erase this one and make it a little neater. So here's my vector v. And then, of course, my line is represented by this dotted line. Now, let's say that we take the vector v, initial point at our known point, and move along the vector v until we're at this point, and then we move along the vector v again. Then the vector from here to here will be 2v. If we go out to the end of this vector and then go in the same direction from the end, half the length of the letter v, of the vector v, then we have 1.5 v. It should be clear that any point now I'm trying to decide how to say this. Any point we can get to by from x naught, y naught, z naught, moving some multiple of v is on the line. And it doesn't take too much thought to at least convince yourself. I'm not going to do a rigorous proof, or maybe I will. We'll see what I say next. That if a point isn't on the line, it's not going to be one of these points. And that all the points on the line are going to be of this form. Pick any point. Here's a point. Now here's a point. How far would I have to go? What multiple of v would take me from here to this point? Looks to me like about 1.2, maybe 1.25. Okay. Make sure you understand that. Any multiple of v will lead you to a point on the line because any multiple of v is in the direction of v. So now I'm going to say, okay, let's just say my origin is here. I'm going to invoke an R vector. And we use a lot of R vectors in this course. And Doc isn't being cooperative. Okay, the R vector from the origin to the point x naught, y naught, z naught is a vector x naught I plus y naught j plus z naught k. Then vector R plus a multiple of v has to be on the line. I better not use C because C is one of the components of V. So I'll use T because T is often used as a parameter. You can think of it as time. Okay, for moving the length of vector V in the direction of V at one length of V per unit of time, then TV will be a vector T times as long as V in the same direction of V. And we can think of T as measuring time. So if it's seconds, 1001 we get here, 1002, 1003, and all times in between. At all times previous, T equals -1, -2, because take -1 times V, we get a vector in the opposite direction and so forth. Okay, so with respect to the origin then, R plus T times V is going to give us a point on the line. Now let's just say we want this point here. And I choose a point over here. Because I want to draw a vector from the origin to this point. If I draw a vector from the origin to any point over here, I'm going to go through my labeling. Purely an accident of the labeling, but perfectly permissible. Okay, so this would be a vector R plus TV for some negative value of T. I would estimate about -1.4. Well, R plus TV we've already said that V is going to be represented by the vector AI plus BJ plus CK. Fairly standard notation seen in most textbooks. R plus TV is then X naught I plus Y naught J plus C naught K plus T multiplied by the vector AI plus BJ plus CK. And of course, by the distributive law, that's just going to multiply A and B and C by T, and we get T times AI plus T times BJ plus T times CK, which equals then X naught plus AT times I plus Y naught plus BT times J plus Z naught plus CT times K. Note that X naught plus AT is a linear function of X. So the I component is a linear function of X. And the J component is a linear function of Y naught plus BT of J. And K component, where the Z component is Z naught plus CT times K. So we can summarize this by the parametric equations. And I don't need the I on there. The equations are x equals x naught plus at, as x is the I component, y is the j component, y naught plus bt, z is the k component, z naught plus ct. So these are the equations that define a straight line, 2 point x naught, y naught, z naught in the direction of v. And it's actually pretty simple. Try to understand every step and every picture here. Okay, well, metric equations for the line. This is a vector equation for the line. I probably should have used R for the sum of these vectors and some other letter here. Now, in any case, this is how you would represent the vector from the origin that traces out the line. So it's another equation for the line. Your book is going to formulate that with a little better notation, but it's the same idea. Then you have the symmetric equations where you solve each of these for t. Okay, so if you solve this for t, well, you're going to subtract x naught, divide by a, and you're going to get t equals x minus x naught over a, which equals y minus y naught over b, which equals z minus z naught over c. So you don't need the t equals, because this is going to be true no matter what letter you use for the parameter. What you have right here is the symmetric equations. For a line. And there are all kinds of things we can do with these equations, and it's fairly easy to apply. Just remember there are three ways, equivalent ways of representing the line, and they all come back to this picture. Okay. We want to talk about the equation of a plane in space. Problem is this, given a point somewhere in space, the point right there, you can see that one. And a normal vector. Let's just take this point and a normal vector in that direction. Then there's a plane through that point perpendicular to this normal vector, meaning that every vector from the point, from the given point, to any point on the plane is perpendicular to that normal vector. That's the idea. So let's draw this as a picture. Let's just say we got the point again. X naught, Y naught, Z naught, and our normal vector. And I'll draw the normal vector with its initial point at our given point. Then a point X, Y, Z is in the plane provided the vector from here to here is perpendicular to the normal vector. So I can write this as a statement. Okay, X, Y, Z is in the plane if and only if the vector from X naught, Y naught, Z naught, X, Y, Z is perpendicular which is got an M. M is close to P in the alphabet. Okay, if this vector is perpendicular to N, now that's equivalent to saying if the vector, well, the vector from here to here is X minus X naught I plus Y minus Y naught J plus Z minus Z naught K. Now let's give N some components. Let's let N again be AI plus BJ plus CK. So N equals AI plus BJ plus CK. Right, this is an IFF if and only if. If and only if this vector didn't leave myself room to write it. All right, a big dot here, dotted with AI plus BJ plus CK. Now, what can you tell me? What's the condition for two vectors to be perpendicular in terms of the dot product? The condition is that the dot product is zero. Okay, so I didn't plan my board space very well there. Kept thinking I was going to have room to write this, but spread it over two lines. There's your condition. So let's call this vector x minus x naught I plus y minus y naught j plus z minus z naught k. I'm not sure it's a good idea, but let's call it v. So v dot n equals 0. That's my equation here. Is equivalent to saying a times x minus x naught, x being naught little, plus b times y minus y naught, plus c times z minus z naught equals 0. Well, this is an equation of the plane. This is an equation of the plane because in each case, point x, y, z satisfies the condition as long as it's in the plane. As long as this v vector here is perpendicular to the normal vector. And if it's in the plane, well, the condition has to hold. So this is the equation of a plane. So here's the equation of a plane. Also down here is the equation of a plane in just different form. Now, suppose we want to find the plane through 3 given points. P equal, we'll call x naught, y naught, z naught, whatever the numbers are, we'll denote them by x naught, y naught, z naught. Q, x1, y1, z1. R is the point, x2, y2, z2. Okay. That ends kind of badly positioned, but it's through P and Q and R. And it's not the way I want to state it. It is through the 3 points, but and we can use any point in a vector perpendicular to the plane. Okay, could use any one of these points. But I'm going to say through this point containing Q and R. Okay, so what is x naught, y naught, z naught? There are 2 vectors in the plane that we can use, and I'm going to use the vector PQ and PR. So we could kind of sketch this. Here's our point P. Here's our point Q. Here's our point R. And we have a vector PQ and a vector PR. Now, if I give you numbers instead of x naught, y naught, z naught, x1, y, and so forth, if I give you numbers, you can calculate, you can tell me what these vectors are. So I'm going to say big idea, real idea. vector n equal PQ cross PR. In other words, just take the components of these two vectors and do the cross product. That vector has to be normal to the plane. Why? Because the cross product of two vectors is perpendicular to those two vectors. These two vectors are in the plane, so vector perpendicular to these two vectors is perpendicular to the plane. Now, there's more that can be said about that, but we're going to leave it at that for now. You read your book, ask in the class, and we can say more about it. Okay, so this vector is normal to the plane, and we have the point P. So we find plane is through X naught, Y naught, Z naught. It's normal vector M. If N equals AI plus BJ plus CK, and if you have numbers for all these things, you can find the vector PQ and the vector PR, and then you can take the cross product and by the right-hand rule and so forth. You get vector perpendicular, and using those numbers, you do this cross product and you get your normal vector. N equals AI plus BJ plus CK, something you can easily calculate if you have numbers here. And there's your equation. A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals 0. So you just have to do this simple process. And of course, I'm quoting what we just did with the equation of the plane. So right there it is. You have the numbers here. You can find the numbers for these two vectors. You can do the cross product to get the normal vector, to get a normal vector. And then you can, having gotten the components A, B, and C of the normal vector, you can write out the equation of the plane. Now you might want to do the dot product and so forth to reinforce, remind yourself of where this comes from. I recommend that you do so. There it is. Okay. Let's say you're given the plane 2 times X minus 4 plus 3 times Y plus 2 minus 5 times Z minus 3 equals 0. What can you identify? Well, this is your A times X minus X naught, you watch Y, it's this, okay? So you can immediately identify normal vector and the point is 4, -2, 3. Because of course, X minus X naught is X minus 4, that means X naught would be 4. And if Y minus Y naught is Y plus 2, that means Y naught had better be -2, and so forth. Okay, so there we have it. Okay, so if your origin is right here, you can move 4 units in the X direction, 2 units in the Y direction, 3 units in the Z direction. Here's your origin now. Here's your plane, or here's a point on the plane. And what's your normal vector? Well, 2 in the X direction, 3 in the Y direction, -5 in the K direction, your normal vector is there. So your plane's up here, with the normal vector here, and there's your plane. Now, you might understand those gestures or not, but make your own gestures, make up your own points. Okay, that's all I'm going to do on this video, and I'm chopping this up into 3 short videos. And I've got limited time. I'm going to have to leave in, 35 minutes. And I want to get these videos processed and downloaded before I leave. Okay, so we're going to do one more video, hopefully time will permit, where we talk about finding intersections of planes, intersections of lines, intersections between lines and planes. If we don't get to that today, we will get to it in class.